everybody for joining. I'll share my screen. Can I just get a thumbs up that's working? Sweet, awesome. Yeah, thanks for joining everybody. My name is Danny Coutts. I'm a research scientist at the Geological Survey of Canada in Calgary. And yeah, today I'll be talking kind of about probabilistic age models and how we were able to use that in a basin setting, but then kind of how we can apply that to tectonics in a lot of different settings. And so these are kind of the co-authors that are on this kind of whole project, and something that we have a mix of like deep water sedimentologists, biostratigraphers, geochronologists, and people that think about really big basin processes. So I think that it goes to show, and hopefully you'll see that throughout, that I think that there's a lot of need for a variety of folks to kind of do this kind of tectonics research. And we're kind of all better off because of it. So yeah, as Taryn mentioned, there we go. This is part of my PhD work at the University of Calgary that we published in 2024, and it won the David Elliott Award paper in 2025, which was a great surprise. And so yeah, here's the title from Geoscience GSA Bulletin, and then there's the QR code if you want to go get it right now. But yeah, we'll be going through a lot of this in kind of other applications. So time is like one of the most kind of important parameters in most geological disciplines. We have a lot of different techniques that are developed to measure the age of either specific minerals or stratigraphic geologic units. So we have geochronology, the measurement of absolute rock and mineral ages through various kind of isotope comparisons, providing absolute ages. Then we have biostratigraphy, correlation of rock units based on the appearance, disappearance of fossil taxa. And then we have magnetostratigraphy, relative age dating, which is the correlation of rock units based on reversal of the Earth's magnetic field. There's some other ones in there, but those are the main ones that we're going to kind of consider. And all these methods have limitations and uncertainties to their use. Geochronology, we have analytical uncertainty based on the actual kind of instrumentation and methodology of that instrumentation that we're using. Within geochronology, we're going to have maximum depositional ages, which are the dating of detrital minerals within like a clastic rock. And we're going to use the age of those detrital minerals to approximate the age of deposition of that clastic rock. And so this is largely limited to coarse grain strata because we're after sand-sized zircon grains or any kind of detrital mineral. And then there's no lower limit because you have to form these crystallization ages, these zircons, for example, erode them, transport them, deposit them, and so the crystallization ages inside the rock provide kind of a maximum limit, and the rock deposition can be anytime after those grains formed. Ash beds like tephrahs or tuffs are largely preserved in fine grain strata. And then for biostratigraphy, we're largely working in fine grain strata where we preserve these fossil taxa. We're not looking in like huge conglomeratic deposits for ammonites. And some biozones are really broad. In magnetostratigraphy, we're limited to where we can really confine and map out these reversals and tie them to absolute ages. So depending on the work you're doing, and a lot of work in geoscience is often quite siloed, that we have these kind of disparate age records around certain study areas. And so Bayesian age methods are a statistical approach, or Bayesian methods in general, I guess, are a statistical approach to update our confidence in a certain probability outcome given new data. So the classic example is you're a doctor, and I'm talking about a medical doctor, not a rock doctor, like a lot of people probably in this talk. But given patients' various test results, what is the probability they have a specific disease? So the kind of starting hypothesis is like the general occurrence rate of that disease in the general population. And then based on new test results and the kind of accuracy of like a certain medical testing method, we can kind of combine these probabilities to update the probability of a patient having a certain diagnosis. And so that's the general idea of Bayes' rule. And there's many Bayesian applications in geology. Today, we're just going to be talking about Markov chain Monte Carlos because I think they have the largest application to chronology data. and they're also generally the easiest to understand. So the Bayesian method that we were applying on the west coast of Canada was published by Sam Johnstone at the USGS in Colorado, published that in 2021. The title from the paper, as well as a QR code if you want to go get that one right now. And essentially Sam and co-authors worked on a way to combine all these different types of geochronology data we have for a single stratigraphic column and create what I like to refer to as kind of like best fit ages. And so when we think about this schematic section from Sam's paper, we have some kind of basement crystallization age, and then we know that through the law of superposition that all these rock units follow each other sequentially. In unit 2, we might have some kind of detrital zircon maximum depositional age. So again, this is the rock unit can be anything younger than the crystallization age of the zircons within it. Then we have a biozone, which is kind of binary in nature, that once we're in that biozone, we know we're within the limiting ages. And then we have some kind of ash bed, which would be Gaussian, where the age is flanked by some kind of analytical uncertainty. And then we have this top unit, which is another tetrahedral zircon maximum depositional age. And so, and based on these constraints, we can kind of limit the age possibility based on these measurements to the kind of white area in the center. And so the way the SAMS methods work is we're going to be drawing samples from a method-specific distribution. So again, magnetostratigraphic and biostratigraphic ages are kind of these binary distributions. Radiometric ages are Gaussian in distribution. And then maximum depositional ages are kind of like these survivor curves. And so these are all different samples that follow the law of superposition. And we're going to start off with a best guess estimation of the age of the rock. And so that could be the middle of the biozone, the actual numeric date of the kind of radiometric age, and then the date of the maximum depositional age. We're then going to determine which samples follow the law of superposition, which ones don't, which ones are, like in this case, we are going from oldest to youngest. So we have younger underneath older, so that's wrong. And then we go all the way up. These are all correct. And essentially, we're going to allow the samples to iterate randomly with like kind of a bit of noise towards following superposition. And this is referred to as a random walk. So we're going to start at our initial sample guess, and we're going to allow it to randomly walk towards being correct. And even once it becomes correct, it's still going to iterate around exploring the different, the kind of data space that's allowed by this distribution of constraints. And so we're going to allow for what we call a burn-in phase, where we're not recording the random walks. And then after a certain point, we're going to start recording the random walks within this distribution. And so if we go back, we start out with our prior knowledge being the red distribution, and then we have all the samples after that burn-in phase that follow the law of superposition in green. And so the red distribution would be your priori, and then your green distribution would be your posterior distribution. And I generally refer to these green distributions as like our best fit ages that follow the constraints that we have in the stratigraphy. And so we saw a huge potential for this method on the west coast of Canada, where we were doing a lot of geochronology and stratigraphy in the Nanaimo group. So the Nanaimo group is a 2-kilometer thick late Cretaceous turbidite channel fill in a kind of 4-arc basin exposed in the Gulf Islands of British Columbia. So we have Vancouver Island on the left, mainland British Columbia on the right, and then we have the lower Nanaimo group in green, and then the upper Nanaimo group in yellow. So the upper Nanaimo group is largely these deep water channels where we have multiple channels making up these islands. And if you need vacation recommendations, please let me know. I've been to a lot of them, and they're all fantastic. So highly recommended as a Canadian vacation destination. The goal of the project was to constrain the fill and age of the channel systems and determine what kind of external forces or autogenic processes were causing the stratigraphic record to evolve the way it did. And so this is the work of 3 grad student theses, myself, Rebecca Englert, and Heather Gray. And so we were out trying to map the different submarine channel systems, figure out if we're in an upslope canyon, somewhere on the slope, or in a fan, look at the cross-cutting relationships of the channels, figure out their relationship to active structures, and then date all of these really accurately to figure out how they relate to different processes that are going on in four-arc basins, like changes in subduction, things going on in the arc, be it underplating or magmatism. And so we need to be able to look at the depositional architecture really precisely, as well as date these deposits very precisely. So within the Nanaimo group, we have originally lithostratigraphic formations that were very rigidly defined as deltaic units, then submarine fans. We reinterpreted them largely as submarine channel deposits. And there's 3 coarse-grained units within the Upper Nanaimo group: the DeCourcy formation, Jeffrey formation, and Gabriola formation. And so these are the submarine channel deposits of different flavors. And then we have Cedar District, Northumberland, and Spray formations that are either the levee, so like proximal overbank deposits. They might be slope deposits, so more distal deposits to the channels. And then we have large mass wasting deposits that are occurring on the slopes as well as in the levees and all that kind of stuff. And again, we're looking at late Cretaceous to early Paleocene deposits. The lower Nanaimo group is all non-marine to like marginal marine, like shallow water deposits. And we'll touch on those at the very end. So as a plucky group of grad students, we went out and we were mapping all these islands, trying to break down the stratigraphy as finely as possible and gather kind of as many detrital zircon samples and as we could to fill our rental cars. And so most of the exposures along the shoreline, so this is Galliano Island and Main Island, and we also have outcrops on the interior of the island. The stratigraphy is really well exposed just in the topography of the islands, and so we have really coarse-grained ridges that make up the kind of axis, the axial deposits of these turbidite channels, so like the really coarse-grained conglomeratic or sandstone fill. And then we have these large recessive bays that are largely filled of those kind of levee deposits or slope deposits. And so the topography itself gives us a great way to kind of attack mapping on the interior of the island once we've kind of mapped our way around the exterior. And so this is just a 3D draped digital elevation model of Galliano and Maine, showing kind of some of the architecture that we were able to draw out of all the different mapping we were doing. So we were able to take that mapping at the surface and then as well combined with structural measurements and paleocurrent measurements and bring this kind of into 3 dimensions. And so here's a cross-section from D to D prime across Gabriola Island, which would be kind of this northern portion. And Gabriola Island is a doubly plunging syncline, so it's kind of like that shape. But that also gives us a great kind of exposure into what the 3D geometry of this system is. So we can have all of our outcrop data, as well as we brought in water well drilling records, and we're able to kind of plot this up in 3 dimensions in a lot of cases. And we can see that originally the Jeffrey Formation on the west coast of Gabriola correlates to fine-grained what we would be calling Northumberland. And same thing that internally within the Gabriola Formation correlates over to a recessive fine-grained bay that was originally called the Spray Formation. And so we can start to show the 3D orientation and geometry of these bodies and are able to constrain the architecture really well. So there's about 6 different flavors of sedimentary rocks as far as like things above a facies association. So the types of channels that are present in the Gulf Islands is we have these low aspect ratio channel forms. So they're like narrower and thicker. They're filled with conglomerate and sandstone, and they're flanked by extensive levee sequences. Then we have, so they're interpreted to be these kind of levee bounded, kind of mid to lower slope channel systems. And then we have these high aspect ratio channel forms that are poorly confined, so they're much thinner and broader, and they stack in very broad channel belts, and they don't really have levees. And so that's kind of an example here, where we have these kind of composite channel packages that are stacking in this kind of broader channel belt. And then we have these tabular sandstone deposits, which we interpreted to be more similar to turbidite lobes. So very much lower slope, very low gradient deposits that are largely depositional. And this is from Valdez Island, where we got a sailor that we knew to sail down. He's also like a professional photographer, and he sailed down and took photos and stitched this huge, like, multi-kilometer panorama for us. And you can just see that these things are like pancake dead flat for kilometers. As far as fine-grained deposits, I mentioned that we have these levee sequences that are much more heterolithic, and then we have these tabular mudstone deposits that are effectively represent either non-deposition between channels or really distal to channel filled, where you're not having overbank sandstones kind of flow out. We do see some evidence of sedimentary faulting within these levee sequences, where you might have like the channel itself be kind of like a void space where these turbidites are coming down the continental shelf, and then you have kind of slumping along some of these sedimentary faults. So we were able to pick out a lot of different flavors of sedimentary rocks and kind of bring those into a very large holistic kind of framework. And so this goes from Hornby Island all the way down in the north, down to Saturna Island in the south. And so we have mapped lithology of all these different units. And then we have kind of how we classify them into those different groupings. So we have DeCourcy channels in green, Jeffrey channels in purple, and then Gabriola channels in tan. And then we've kind of grouped them based on how they stack. And so we can see there's a variety of different channel types at different times in large kind of overlapping sequences in the south. And we say that there's more or less 3 areas of channel activity in the northern, the central, and the southern part of Basin, with this big Gabriola channel belt kind of spanning between them. So that's how we did the depositional architecture really precisely. And then to do the depositional age, I'll just flip back. Each one of these callouts that is a white circle with a number is a maximum depositional age that we grabbed from all over these channel systems. And we gathered about 37 of them from largely the top and the bottom of the channel units, collected 300 uranium lead dates per sample at the University of Calgary Geo and Thermochronology Lab on a laser ablation system, calculated their maximum depositional age, and we brought them into 2 of these Bayesian Monte Carlo models, one for the northern portion of the study area and one for the central portion of the study area. And so this is the example for the northern portion. So we have biostratigraphic, magnetostratigraphic data, and maximum depth, tetrahedral zircon maximum depositional age is kind of intercalated throughout. And so additional age control was not available in the southern portion of the basin, which is kind of makes this tricky because now we're in an apples and oranges kind of scenario. And so what we decided to do was we decided to use the results from the posterior distribution, the kind of best ages that we can get from the model, given all the constraints, to assess how accurate our maximum depositional ages are. And so here we have the posterior age distribution, our original maximum depositional age. And if we subtract the 2, we get an uncertainty or error distribution. And so stacking up all of our error distributions, we get a general error or uncertainty mode of like 500,000 years, which is pretty good in the late Cretaceous. And so we were able to say in the paper that we believe that our maximum depositional ages are a valid way of dating these rocks. So taking that big basin cross section and blowing it up into time, so we no longer have thickness on the y-axis, we have time, we can start to see how these rocks are separated in time, and we have actual chronostratigraphy. So our Bayesian kind of posterior age distributions are shown in violin plots, whereas our maximum depositional ages are shown just as rectangles here. And we can see that the Coutts formation is pretty diachronous across the basin. Starts earlier in the south and kind of continues once we hit about 75 million years. And then we have this big Jeffrey conglomeratic event that is around 72 to 70. And then we have Gabriola deposition at the top. We can also create time slices with our paleocurrent data to look at where and when these channels are active and where they're sending sediment down into the deep ocean. And then we can bring these best estimates of channel activity into a context of allogenic controls. So we have our 3 sediment fairways, each with their own channel history. And so we can do the classic thing of trying to tie deep water channel evolution to sea level, where we're going to start looking at a eustatic sea level curve in black and trying to figure out if there are certain like drops in sea level that are correspondent with erosional or kind of depositional periods of deep water channel deposition. But the along strike nature of what we see in the Nanaimo group kind of says that there's other factors at play because there's just too much going on in different places that aren't kind of homogeneous to the sea level curve. We can look at thrusting within different parts of the Coast Mountains or Western Cordillera. And that might be the result of this kind of really conglomeratic deep sea channel deposition in the Jeffrey Formation, where we have all 3 channel belts are contemporaneous with the same type of channels deposition, really conglomeratic, like microwave-sized boulders rolling down these things, and is coincidence with the very southern portion of the Coast Mountains and the basal portion of that undergoing contraction. There's also kind of like a spurious change in the subduction parameters of the Kula plate at that time, so maybe that's one driving the other, driving the next. And then lastly, we have a large change in turbidite channel orientation from kind of basin margin transverse to basin margin parallel that we see in the Gabriola Formation. And that's coincident with Kula plate subduction parameter changes that might be driving active structures in the forearc, changing this from these big levee-bounded systems to like kind of a large channel belt. And so when we think about what this kind of joint stratigraphic sedimentological and geochronological approach allows us to do, it gives us a very high resolution view of the basin. And it gave us a way to test the accuracy of our maximum depositional ages by using the biostratigraphic and magnetostratigraphic data in a very novel and kind of unparalleled way. So we can kind of take our initial ages and refine them using other constraints to see more in a more detailed fashion what is going on. And so when we think about how we can apply these Bayesian Markov chains in other instances across tectonics research, petrochronology involves the integration of rock and mineral geochemistry and geochronology to understand rock forming processes. So this is an example of a paper where the authors are taking monazite ages, and so you have different monazite domains on this laser map that they've kind of translated here. And by dating and looking at the chemistry of those different domains, we can plot out a potential kind of temperature path through. And because all of these kind of analytical measurements come with uncertainty, you can see that they overlap in a huge field in the early phases because of the clustering of these ages, and as well as kind of just all the uncertainty. And so Bayesian Monte Carlos are kind of a way that we can plot the best fit through that rather than just trying to fit some kind of flexible regression through it. Because there might be more parameters that we want to take into account rather than just some kind of linear regression. And then when we think about tectonics, especially in a basin sense, modeling of ancient basins and their subsidence or deformation requires the use of a lot of different techniques or a lot of assumptions like the porosity or the thickness of these units, their age constraints. And so this is some work from Svalbard where they used a Bayesian Markov chain Monte Carlo to look at a distribution of potential basin models, taking into all the kind of uncertainties and all these assumptions. And then they end up with a distribution of, in this case, this is a stretching parameter for basin subsidence. And you get a distribution that is probably more indicative of the range of possibilities rather than a single subsidence curve. So in summary, Bayesian methods allow us to update prior notions based on new evidence. In the Nanaimo Basin, we use Bayesian age models to refine and test the accuracy of our maximum depositional ages, which was key because we were going to hang our hat on them for all these kind of larger interpretations of what's going on the west coast of Canada. By doing that and refining these ages, we were able to see that the synchronous lithostratigraphic formations were sometimes very highly diachronous and sometimes overlapping with other formations in the time of their deposition. And we were able to link the stratigraphic evolution to subduction parameters in Cordilleran evolution. Other applications of Bayesian approaches allow us to bring in multiple lines of evidence to be tested and the uncertainty in a lot of these assumptions to be examined. And then one last thing about the upcoming Nanaimo group work is the University of Calgary, when I was doing my PhD, was working on the upper Nanaimo group. And then Simon Fraser University was working on the lower Nanaimo group. This is what the stratigraphic column looked like when we started. The last stratigraphic column was kind of worked on or drawn up in 2013. And then this is what our view of the basin is now. So we can see that there's a huge range of different processes going on at the same time that largely violate the laws of lithostratigraphy in these settings. And so it's a very interesting problem to be working on. And I think that when we think about tectonic research in Canada, we're often working in, say, a greenstone belt here and there, or parts of the Cordillera. And we often have a view of the stratigraphy that is very much just a weathering profile. It would be some kind of lower flow basalts and then some kind of gray wacky package on top. But there's a whole lot of different processes going on in these basins and in these very complex tectonic environments that need to be sorted out. And so bringing in a more kind of robust computational approach is sometimes worth it when we can start to refine these ideas. So that is all for me. Thank you for your time and interest. And I'd love to chat about where people see these approaches, where they're using them, and yeah.